Alright, see if we've got this down pat now. Try it again. So what again was the area of the circle? Pi r squared. I'm back in area now. That would be, in radians, the angular rotation would have to be 2 pi. Alright, that's what I had up here for a moment. Okay, let's do the area of part of a circle. Why did I write what? Not delta, that's theta. That's the symbol. This is the symbol for the angle of rotation. So I don't have to write this over and over. But we've been using this for 2 chapters almost now. That's the symbol we introduced when we went from the sign in a triangle to the sign in in rotations. We use theta. So let's call the area of part of a circle A, and we'll call the angle of rotation the angle of rotation. So the part of the circle is to the overall area as the angle of rotation is to 2 pi. Does that make sense? The whole circle has an angle of rotation of 2 pi. Part of the circle will have an angle of rotation that's unknown. Well, if you solve this, so if you do A times 2 pi is equal to theta times pi r squared, and then you're going to do what? To find the area of part of a circle, you would divide by 2 pi, right? Pi cancels. And so we get a 2 in the bottom here. Well, that's just a half times the angle times r squared. So the whole symbol pi disappears. So that's an easier formula to work with. The area could also be a half times the angle of rotation times r squared. Okay, and that will be what goes over here. Now that is on your formula sheet that you have at some point. So how do you use this? Well, you just plug this stuff in. Find the area, and it's called the area of a sector if we only go part of a circle. So a sector is part of the circle. If the radius of the circle is 4, and the central angle is pi over r. So which symbol do I put above central angle? Is it an A or a little theta? It's a theta, right? So the angle of rotation is also known as your central angle, because a central angle, we looked at that real quick, but this is a central angle, isn't it? Vertex in the center of the circle and the endpoints on the circle. Okay? Or it intersects the circle. So can you just plug this one in? It's a half times, let's see, I have theta first. So pi over 3 times 4 squared, which would be 16 pi over 6, which is 8 pi over 3 meters squared, which is sort of awkward. I've never seen anybody or heard anybody say, hey, 8 pi over, so 8.4 meters squared. If the radius isn't known, but you know the angle, and you know the area, should you be able to find the radius? I think so, because if you look at your formula, how many unknowns are left when you know 2 out of the 3? How many unknowns are left? Anybody? How many unknowns are left? Just 1, right? Okay, so 1 unknown you should be able to solve. So how do you solve this? Yeah. What would be your first step? Can you get rid of the half?
Yeah.
Multiply by 2? Yeah? Then what? How do you get to r squared by itself? can you do there? Okay. So you use the reciprocal. If you multiply by 3 over pi, pi here and there cancels, the 3 and the 3 cancels, but you do have to do it on both sides. And then that means that your radius will be the square root of that mess, right? Okay, so I'm trying to get to the point where I only have one thing to put in the calculator, which this would be it. So this is my best. I'm sorry, Ashton, I didn't hear what you asked.
Why did you do the 3 over pi?
To get r squared by itself.
No, we already did that.
No, not initially. I had pi over 3 times r squared, so when I multiply by 3 over pi on both sides, look, it's still here. Okay, it is there. It did change the left side, I just wrote it a slightly different way. Okay, so that's your radius. Okay, moving on to your favorite belt pulley problem. Right, D? D. So how do we do this one, D? Since apparently that one wasn't interesting enough. Pay attention. That's annoying. I'm going to divide this thing into 4 areas. Some of those are easy to find, some of them are a little bit harder. In case you're wondering where the 1.37 comes from, so angle DAE is listed here as 1.37. That's already in radians. The reason I know that is because they didn't put a degrees on there, right? And it's clearly not 1.37 degrees or 137. But we got that from the previous notes. So that's from the previous notes. Except I did everything in degrees because degrees think easier for us. So the conversions here are already done for us. The reason we have these conversions is because if you look in this formula, guess what theta has to be in? For this to work, theta probably has to be in, not in degrees, in radians. That was the whole idea. We converted everything so that it is expressed in radians, the same as we did with the arc length. We converted it so that theta was no longer an angle of rotation in degrees, it had to be in radians. So the area that I'm interested in inside the belt system would be area 1 plus area 2 plus area 3 plus area 4, and then what do I do to that whole mess, D? Huh? Is that enough? Once I find the top half, I need to multiply by 2. Okay. Can I find area 1? Well, I hope so. Do I have everything that I need for area 1? Well, the half is given. The angle is 1.37. The radius is... Okay. Get a calculator. And if you do that, you should have 17.125. How do you find area 2? Well, that's just a rectangle, isn't it? So base times height. So 5 times 6 squared is 6. That's 30 squared is 6. Area 3 is a right triangle. Keep in mind that these angles here are all right angles, right? Because they're tangent, line is tangent, so that radius is perpendicular to the tangent. Same thing here. That one's also perpendicular because we made it parallel. So we have a right triangle, and for right triangles the area is actually pretty easy. It's a half times base times height. So it would be a half. If we call 3 the base, then the height would be that 6 squared is 6. So that would be 9 squared is 6. And area 4 is another sector, so it's another half times theta times r squared. And again, the angle is fortunately given to us, so it's just a matter of plugging all this mess in. and then the radius here would be 3 plus 5 is 8. And if you put that one in the calculator, it's 56.64. So the total area is 169.2951. So just add all these together. So when you add this mess, take out the square roots, so just put it in your calculator. And I have a little more decimals than I need. And then that needed to be multiplied by 2. Did I say 1,000? I meant to say 100. I think I said 1,000. Okay. The trick here would be that what if, we didn't have these angles? So that's basically the problem that I did on the board rather quickly, but you can find these angles and you can find it, and it just hinges on, you can find this angle over here or this angle over here because you have a right triangle with two sides that are given. So based on this angle, actually this angle, because it was just 180 minus x, and this one actually is the same as x. So you can find all the missing parts by just, one little trick function or two maybe, by looking at the right triangle in the middle. Okay, so there's not a lot there. I just wanted you to see that connection. Okay. This one, I'm not sure how far I'll get with this, but this one's a little more difficult or different. So the segment is the shaded part. Okay, so that's the area of the circle that's shaded, so that would be the area of the sector. So the segment area is the area of the sector, so that's part of the circle, minus an area of a triangle. You guys see how if I take this whole sector, and I'll sort of try to trace it, so if I take the whole sector given by this, like on the inside of the red, and then I take out the area of the rectangle, or sorry, the triangle over here, and we erase all this here in a moment, then that would be the sliver that I'm looking for, which we call a segment.
Wait, okay.
Do you guys see that?
The segment is the shaded part.
Yes.
And you're only trying to find that?
Yes. And the way that I'm going to do that is I'm going to find the area of the whole sector, so the whole thing that is inside this little squiggly line, and then I'm going to subtract the area of the triangle that would leave just that, right? Yeah. Okay. So let me erase all of this stuff. All right. So that completely hinges on finding theta. So if I could just find theta. How can I find theta? Law of cosines. Very good. Because you know that 3 squared is equal to 2 squared plus 2 squared minus 2. There are a bunch of 2's in here, so I'm sorry for that, but I try to do the same problem that the book did. So the cosine of theta. So let's see if that's, if we call this a and then we call this b, this is your a squared plus b squared minus 2ab. It's just that everything here is a 2, so it looks a little funky. Okay, it doesn't necessarily all have to be 2's, there could be 5's, but you still have a bunch of them that are the same. If you solve this, then the cosine of theta would be a negative 0.125. Is that a reason to sort of have, that's okay, right?
Yeah.
The negative just means you have a, negative means we have an angle larger than 90, which the picture looks like it's more than 90, so that's actually good. Okay, now I actually solved this one in radians. Okay, so I put my calculator in radians mode and took the cosine, the inverse cosine of that. You can do it in degrees. It would be the same thing, except you'd have to do times 180 divided by pi. So what's the area of the sector?
Should we leave our calculators in radians now?
You could. It would probably make some things easier. So the area of the sector would be this thing, right? So that would be a half times 1.7, and then the radius of the circle is 2 squared. So that gives you 3.4. How do you find the area of the triangle? Can I just use a half AB sine C? Don't I have this angle now? I have this angle, and if I call that C, then I have the two sides that are to the side of it. Isn't that a formula that we have? a half times 2 times 2 times the sine, and this can be in radians, guys. If you leave your calculator in radians, you just plug in sine of 1.7. If you do that, it's 1.98. And what do we need to do with the two things here? What we're going to do to find the segment area? Right, subtract it. Okay. So I know this was a little fast. The main idea here is that you understand that you can do this. So that's step 1. Step 2 is you can find the angle, and then after that it's stuff that, well, today's new to find the area of stuff, but it's then stuff that you hopefully can do. It's the little parts, and then how do you put it together? That might be the problem. So let's just pretend it's at inches squared for this one.